Hey everyone, and welcome. Today we're going to tear into a really fascinating paper that challenges one of the core ideas in AI, the whole concept of randomness. It suggests we can move from just chaotic chance to something more like intelligent design. And honestly, the results are pretty mind-blowing.
Okay, so to really get what's going on here, we first have to set the stage with two big approaches in AI. You've got deep learning over on one side. We all know it. It's incredibly powerful, but boy, is it slow, complex, and it just eats up mountains of data. And on the other side, you've got this alternative called broad learning systems, or BLS. It's built for speed, efficiency, and it gets the job done without needing a ton of data. So, what's the secret sauce for BLS? How is it so fast? Well, it all comes down to randomness. Instead of spending ages carefully training all these deep, complicated layers like a deep network does, BLS just generates a whole bunch of features using random weights. It completely sidesteps that long, heavy lifting training process. Now, that speed is awesome, but it leads to the big question, the one right at the heart of this paper. Is just pure, unguided randomness really the best way to go? The researchers behind this started to think that maybe, just maybe, there's a hidden downside to all this chaos. And it turns out they were right. Pure randomness has some real problems. This kind of randomness, the technical term is independent and identically distributed, or IID, it can be really redundant. You end up with a bunch of features that are basically doing the same thing. Worse, they often miss the real patterns hiding in the data, which leads to what the paper calls spurious or scattered, noisy results that just aren't very effective. So, this is where things get really cool. The researchers didn't just throw randomness out the window. Nope, they decided to give it some structure. And this is their big idea, their core innovation. A new method they call Structured Broad Learning Systems, or SBLS for short. The idea behind SBLS is actually pretty simple, but it's incredibly powerful. Instead of pulling features out of thin air, out of pure chaos, it uses a predefined structured pattern to guide how those features get created. The paper calls this pattern a basis, so we're moving away from pure randomness to designed randomness. Think of it like this. The old way, the classic BLS, is kind of like trying to paint a picture by just randomly flinging paint at a canvas. You'll get something, for sure, but it's going to be messy, unpredictable, chaotic. But SBLS is totally different. It's like using a stencil. You've got this nice, predictable shape, like a smooth curve, as your starting point. You're still using randomness, maybe to decide exactly where to put the stencil or to add some variation, but it's all guided by this intelligent pattern. You end up with something that's controlled and actually meaningful. So, what is this basis thing anyway? It sounds complicated, but it's really not. It's just a mathematical function that's already defined. The paper looks at common ones, like those smooth Gaussian curves or S-shaped sigmoid functions. The key here is that this basis gives the model what's called an inductive bias. It's like a helpful hint, a starting point that nudges the model to look for certain kinds of patterns, helping its neurons to specialize. Okay, great theory, but does this clever idea actually get better results in the real world? The paper comes back with a huge yes. The experiments show that this structured approach has three really clear, really powerful benefits. So what are they? Well, for starters, SBLS is more accurate. It's also way more robust when you throw noisy, messy data at it. And maybe the most fascinating part, the model actually becomes easier for us to understand. That's a huge deal in AI called interpretability. Let's look at the proof. Here we have the famous M- dataset. The task is recognizing handwritten numbers. The classic, totally random BLS does pretty well, hitting an F1 score of about 96.9%. But SBLS, using that Gaussian basis to give its randomness some structure, bumps that score up to almost 97.4%. And trust me, in machine learning, that's a really solid jump. But it's not just about getting a higher score. It's also tougher. The researchers started messing with the data, adding a lot of noise, which happens all the time in the real world. SBLS just handled it way better, keeping its performance steady while the classic model struggled. This structured design makes it so much more resilient. And this slide, this is where it gets really interesting. This is that interpretability I was talking about. When you ask both models, hey, which pixels helped you recognize the number 3? The classic BLS points to this scattered, noisy mess. It makes no sense. But look at SBLS. It highlights the pixels that clearly,
perfectly form the shape of a 3. It's learning patterns that we can actually understand.
And that brings us to what might just be the most powerful idea in this whole paper. Because SBLS uses a predefined basis, it means we, as humans, can actually step in and design the features that the AI learns from. The paper says it perfectly right here. We can take our own knowledge about a specific problem and build it directly into the model's design. Think about that. If you're an expert in something, you can give the AI a massive head start by encoding your expertise into its very structure.
And they didn't just talk about it, they did it. They took the MNIST problem and said, okay, we know these digits are made of lines and curves on a little grid, so they designed a custom basis with functions that are really good at spotting exactly those kinds of shapes. It's literally like telling the AI, hey, you should probably look for things that look like this. And what was the result? Bam, look at that number. By injecting that human knowledge, that custom design basis, they pushed the accuracy even higher, all the way up to a 97.75% F1 score. It's just definitive proof. Intelligent design beats pure chaos, hands down. So let's zoom out for a second, because this is about way more than just one algorithm. This could represent a real shift in how we think about building AI systems from the ground up. What we're seeing here is a move away from just chaotic exploration, where we basically throw a ton of randomness at a problem and just hope something good happens, and a move towards a much more controlled, intelligent design process, where we're active participants in shaping how our models learn. And at the end of the day, as the paper says, this isn't about making our models bigger or more complicated. It's about making them smarter. By intelligently generating features, we can get better performance and more robust models without having to pay the massive computational price of just making everything deeper and wider. It's about working smarter, not just harder. And that leaves us with one last big question to chew on. For years, pure, unstructured randomness has been this fundamental, untouchable building block of AI. This paper shows that not only can we touch it, we can actually redesign it and make it better. So it really makes you wonder, what other fundamental rules of AI are out there just waiting for us to intelligently rewrite them?